Who can remember the phases of materials? Yes. So, in these three phases, everything consists of matter. Matter consists of particles, right? These particles have a mass and a volume, and they always move. Between these particles, we have intermolecular forces. Yes.
Can you please use a different color?
I can. Better? Okay. Is Antoinette here?
Yes.
Is this you? Who? Who's an Antoinette? Oh, you sneaky. No, I'm kidding. No, it's fine. You can stay there. What is the intermolecular forces? Do you know? Okay, intermolecular forces. What is a molecule? Molecule is two or more elements that's bonded together. For example, water. So water is a hydrogen. Sorry? Water is a molecule. Like one water molecule is a molecule. What do you mean? Sure. Okay. Sorry?
Mom. Oh no. Oh, I said, can you please repeat that?
Okay. A molecule is two or more elements bonded together. Okay? Inter means between. And forces is a force, right? So intermolecular forces are the forces between molecules. Okay. There are different types of intermolecular forces. The London forces, it's intermolecular forces between symmetrical molecules. A symmetrical molecule, for example, is NH4. Let me just make sure. No, not N. I'm sorry. CH4. CH4 is symmetrical because when it bonds, C on the periodic table is in group 4, right? Which means it has 4 valence electrons, right? So it has 4 valence electrons. H is in group 1, so it has 1 valence electron, right? So there's a H that bonds in each open space at the C. Do you see? So this molecule is symmetric. If you cut it down here, this side looks the same as the left side, right? If you cut it down here, the top side looks the same as the bottom side. So it's symmetric. Makes sense? Then we have dipole forces. Do you guys know what a dipole is? It is weak intermolecular forces between polar molecules. So, a polar molecule is one that is not symmetric. For example, water. When we draw the water's Lewis diagram, it's a O bonded with two H's. Oxygen is in group 6. So it has 6 valence electrons. 1, 2, 3, 4, 5, 6. Right? H is still in group 1 and it has 1. Okay, so as you can see, this is not symmetric. If we cut it down the middle, the left side does not look like the right side. So this molecule is going to have some sort of polarity at a side. So this side of the O will be a little more negative, and this side will be a little more positive. Okay. Does everyone understand? Yes. Then hydrogen bonds is bonds between hydrogen and N, O, and F. Okay, that forms hydrogen bonds. This is very important. With gases, the intermolecular force only has an effect at very high pressures and very low temperatures. Does anyone know why? For intermolecular forces to have an effect on molecules, it has to be close to each other. When gases are at very high pressures, they are close enough to each other to feel each other. But when the pressure is too low, the molecules are too far from each other to feel the effects of the polarities on each other. Does that make sense? And the same with very low temperature. If you decrease the temperature enough, the gas molecules get lazy. So they scoot together. Then they're close enough for intermolecular forces to be present. Okay. Kinetic molecular theory. So this theory determines the behavior of a gas. All gases, like all other materia, consists of particles. These particles have a mass and a volume. They are far apart, and gases can be compressed. Does that make sense? Because there are so much open space in between gas molecules, you can squish them together. Okay, if the particles are far apart, they exert no force on each other, except when they collide. When they collide, they give each other some energy. So energy goes from one molecule to another when they collide. Because they all are moving, they have kinetic energy. With every collision, there is no kinetic energy lost. So all the collisions are elastic. Any questions? Refuge is refuge here. Okay, do you know what an elastic collision is now? Yes. So the molecules collide, but no kinetic energy is lost. It's only transferred from the one to the other one. Good. Standard temperature and pressure. Who knows why there is or needs to be a standard temperature and pressure? Anyone want to guess? Why does there need to be a standard temperature and pressure? Yes, exactly, for experiments. So, let's say we just learned that. Did we just learn that? We learned that gases don't behave the same way at different pressures and temperatures, right? Because at very high pressures and very low temperatures, gases have intermolecular forces. But at low pressures and high temperatures, gases don't have intermolecular forces. So let's say we do an experiment with a gas, and it's about 18 degrees here now, right? And someone in the North Pole does an experiment with a gas, and it's very cold there. Let's say minus... You're 150. I don't think it's that cold. Let's say minus 30. Okay. So the gases would behave a lot different at the North Pole than here. So even though we were doing the exact same experiment, we would get different results than they would get, right? So that's why we said, or the scientists said, there is a standard temperature and pressure for experiments with gases. That temperature is 0 degrees Celsius and 101.3 kilopascals. This is just atmospheric pressure. And 0 degrees Celsius is freezing point of water. Then, at these conditions, at standard temperature and pressure, 1 mole of any gas is always 22.4 decimeters, or 22.4 liters. So it doesn't matter if it's helium or hydrogen. If you put it in a container at 0 degrees Celsius and atmospheric pressure, it will always be 22.4 decimeters. Okay. Then if we need, sometimes we need to take the temperature from degrees Celsius to Kelvin, and this is how you do it. You just add 273 to the degrees Celsius. Okay. So these are just some interesting facts. Absolute zero is the coldest temperature anyone has ever recorded. So it's the coldest known temperature. At this temperature, there is no kinetic energy of gas molecules. So every known gas at this temperature doesn't move. They just stand still. So they have no velocity and they have no kinetic energy. Mm-hmm.
If we ever hit that temperature, would we die?
Yes. I think everything would die. Because if you don't have energy, you can't live. And nothing would have energy. So everything would die. Okay? And then at 0 degrees Celsius and 0,006 kilopascal, something happens with water. It's very interesting. I'll show you a video at some point when the Wi-Fi is working again. But at the triple point of water, water exists as a solid, a gas, and a liquid at the same time. So at the same time, water is evaporating and freezing, and melting and freezing and condensing, all at the same time. It's pretty cool.
Can you see it? No Wi-Fi.
Yo, let me check.
No, like I'm asking if you can see it, if you would do it.
Yeah, you can see it. No, it's still not working. Okay. Then for volume and pressure conversions, from centimeter to decimeter, it's times 10. But we now need to remember that when there is a cube, when it's centimeter cube, you have to also times 10 to the power of minus 3 or 10 to the power of 3. Depends on what you want to do. Does it make sense? Do you guys want to do an example of the conversion? Are you okay? Do you want to do one? Okay. So let's say we have something. We have a volume of 21,3 decimeter cubed, and we want it in meter cubed. So we're starting here and we're going there, right? So what do we need to do? Yes, so we're going to follow this arrow. So we're going to say V new is 21,3 times 10 to the minus 3. Then you can put that into your calculator, or you can use it just like that. And just say 21,3. If you put it in the calculator, it will probably give you 2,13 times 10 minus 4. If it's in scientific mode. Okay, the pressure conversion. Does everyone understand the volume conversion? Yes.
I got 2,13 times 10 to the power minus 6.
Oh, okay. That also makes sense. Okay, does everyone understand? So for pressure conversion, when you go from Pascal to kilopascal, you times 10 to the minus 3, or else you divide by 1,000. from kilopascal to pascal times 10 to the power of 3 or times 1,000. There's a relationship between the temperature and kinetic energy of a gas. What happens when you increase the temperature of a gas? The what? Yes, but why?
Because it gets warm.
Yes.
The intermolecular forces start moving faster.
Almost, not the intermolecular forces, the molecules start moving faster. So when the temperature increases, the molecules take the heat energy from the temperature increase and apply it onto themselves. And when they take energy, they convert it to kinetic energy and they start moving faster. Okay. So the temperature of a gas is a measure of the kinetic energy. If the temperature increases, the kinetic energy increases. So when a gas is heated, the gas molecules absorb the energy and the average kinetic energy increases. We can also say that the temperature of a gas is directly proportional to the average kinetic energy. So this leads to the following facts. At 0 Kelvin, or absolute zero, you remember where there's no more kinetic energy, the gas molecules will no longer move, so there's no kinetic energy and no pressure. Inside a container, all the particles are moving at different speeds. And if they collide with each other, one gives off a little bit of kinetic energy to another, which either increases or decreases the speed. So let's say one particle is moving very fast and another is moving very slow. They collide. The one that's moving very fast gives a little bit of energy to the one who's moving slow. So the one who's moving slow now increases speed, right? So the kinetic energy changes between the molecules, but overall, the average kinetic energy stays the same because we have elastic collisions. Right. So, different speeds inside, but the average speed will remain the same. And the average kinetic energy will also remain the same. Okay, homework. Notes number 1 to 3 for tomorrow, please. Okay, this Boyle's law is what your experiment is going to be about. This little piece. Okay. So Boyle's law says that when a fixed quantity of gas is placed inside of a container, it spreads out and fills the container. Okay? So it doesn't matter how big the container is, the gas molecules inside the container will spread out to fill the container. Okay? The pressure inside of the container is determined by the amount of collisions that the particles makes with the container. So if there's 3 particles in a container, there will be less collisions with the walls of the container than if there were 3,000 inside of the container. So more collisions means higher pressure. Okay? Number of collisions of the gas determines the pressure inside of the container. If the volume is reduced, the number of collisions will increase. Does that make sense? So if you take the same amount of gas in a big container and the same amount of gas in a smaller container, the pressure in the smaller container will be bigger because there's less space to move around inside, so the probability of it hitting the container is higher. Okay. So this is exactly what Boyle's law says. It says that the pressure of a gas is inversely proportional to the volume. And this is only true if the temperature remains constant. And we will be using this formula. All right, let's see if this is actually true. So we have 2 graphs. Graph 1, they did an experiment to test the pressure of a gas at a certain volume. Okay, and they got these results. So at a pressure of 100 kilopascal, the volume was 14. And a pressure of 70 kilopascal, the volume was 20. So now let's look at what happens to the graph if you put the volume under 1. So if you use 1 over V instead of V. What is 1 over V1 if V1 is 14? What is 1 over V1? Does anyone have a calculator? Hmm? Mm-hmm. 1 over 1/4. 1 over 14. What's the answer? What is 1 over 14 in decimal places? Sorry. 0. Sorry. And 1 over 20? Okay, so let's plot it against each other and see what happens. Okay, the pressure 70 and 100. 4.
The first one is
2. Yes. Okay. So the first point we need to plot is P1. So P1 is 100 and V1 0.07. So we'll line up V1 to here. The next one is 70 and 0.505. So we'll line them up. $70 and 0.5. Does it make sense? Okay, let me show you how so this is 20, 40, 60, 80, and 100. Is that better?
What are we counting in?
20. Every second block. So every block is 10, but there's not enough space to write everyone. Okay? So 70 would be in between 60 and 80, and 0.05 is this one. So there's where we're going to put the point. Everyone understand? Okay, we can't really know what is happening now, so we need one more point. Do you think that they both go through 0? Can 0 be another point? If the pressure is 0, what will 1 over V be? Are you sure? You're right, but why? So, pressure is inversely proportional to volume. So if pressure goes up, volume goes down. And if pressure goes down, volume goes up. So when the pressure is at 0, it's at the minimum. It cannot go lower than 0. So if P is at the minimum, that means V must be at the maximum. Alright? So V is infinity, because that's the maximum volume. Right? So what is 1 over infinity? It's close enough to 0 that we can just say it's 0. Do you want to test it? We don't know infinity, but we can get close to almost infinity. So take out your calculators and put in 1 over 1. Yes, 1 over 10. The decimals. 1 over 100. So is it getting bigger or smaller? Yeah, so the higher number we put underneath, the smaller the actual answer is, right? So let's do 1,000,000. 1 over 1,000,000. It's, yes, very close to 0, right? Let's do 1 over as many zeros as you can do. Okay, stop. Yeah, it's very small. You don't even know how small. So we can just say 1 over infinity is, it's 0. It's close enough. So the graph that forms is a line. Ah, yes, as straight as I can draw it. So what's the shape of this graph? Yes, straight line or linear. What's the shape of the first graph? It does curve, yes. It's a hyperbola. Mm-hmm.
So what happens? How would you know if it should be hyperbola or linear?
So this one, what do you mean?
Because
So
are we not proving that if volume increases, pressure decreases?
yes.
It's same as the graph that we did on the
Yes, so these are exactly the same, but this one is only volume. It's pressure against volume, but this one is 1 over volume against pressure. So this one, if pressure and volume were directly proportional, meaning pressure goes up, so volume goes up, then this graph would have looked like this. But since this graph wasn't a linear graph, we tried this one to see maybe they're inversely proportional. And then we saw that a straight line was formed, and that means that they are inversely proportional to each other. Okay, so what's the conclusion? We actually already said it. The graph is a straight line, so the pressure is directly proportional to 1 over V. And that means that as pressure increases, volume decreases. Does that make sense? Do you guys want to know why we know this?
Yes.
Why does a straight line give us this conclusion? So, as we know, a straight line formula is y equals mx plus c. Okay, so the m of this would be, what is the equation of the gradient? y2 minus y1, x2 minus x1. And then we get y2 minus y1 is p2 minus P1, and x2 minus x1 is 1 over V2 minus 1 over V1. Since it goes through the 0, C is 0. I'm not gonna have enough space. Okay, so since C is 0, it becomes y equals mx. Y is P. Yes. Let's see. It connects, but it doesn't want to play. Mx is V. Okay, we'll finish tomorrow. Physics. Actually, sorry, no, chemistry.